In today's video, we're going to introduce the concepts of eigenvalues, eigenvectors, and take a short introduction to PCA, which is Principal Components Analysis. We've talked quite a bit about changing basis. We talked about rewriting our data using a new set of variables or a new basis. But the natural question on your mind should be, how do we choose this new basis? Well, one very popular method is to start by choosing basis vectors as directions in which the variance of the data is maximal. Now, this concept of directional variance is not one that you've been exposed to, most likely, before. But if you were to look at this data cloud of these green points, and I asked you, what direction is the greatest spread of the data, chances are just intuitively you might say, along that direction where the line has been drawn. Well, that would be correct. And what we would do next is choose subsequent directions for the subsequent axes that are orthogonal to the first and have the next largest variance. Of course, when we're in this two-dimensional image, we only have one choice for that direction of next largest variance because it has to be orthogonal to the first. Keep in mind, this arrow here points to the northeast. It could easily have pointed to the southwest, and it would be claiming an equivalent direction. And the same with this second arrow could have pointed to the southeast, and you could make an equivalent argument that those are the directions of maximal variance and the secondary direction. Now, when we talk about directional variance, we're talking about the variance of the data once projected onto that direction. So if I take these green points and I project them onto the first vector that we chose, that's what I mean by directional variance. It's the variance of the data in that direction. So that's one example of directional variance. We could also project this data orthogonally onto our secondary direction, and we would see that the spread of the data along that line is much more minimal. And just thinking about this further, we could also project the data points onto the y-axis, the original variable, or the x-axis, again, the original variable. But the place in which we have the most spread of these data points is this direction that we chose as the direction of maximal variance. We chose it intuitively. Now, it turns out that eigenvectors of the covariance matrix will provide these directions of maximal variance. You'll recall from our 90-minute primer that any elliptical distribution is defined by a mean, be the center of it, and a covariance matrix. And that covariance matrix is what really determines the shape of that data cloud in space. So eigenvectors are the major and minor axes of the ellipsoid. That would be this shape here that would kind of contain our data, that's associated with that elliptical distribution defined by a given covariance matrix. These VI vectors here are unit vectors, meaning they have length 1, just like we want from an orthonormal basis, and they are just specifying the direction. And the lambda I are scalars that actually indicate the magnitude of the spread. So they tell us the variance of the data in each corresponding direction. By corresponding, I mean that lambda 1 is the variance along V1, lambda 2 along V2, etc. Great. So, I've already brought up the terminology, eigenvector. What is an eigenvector? We're going to walk through a definition, and it's a simple definition, but its connection to the broader picture is more difficult. And it's actually a connection we won't make. But if we're going to talk about eigenvectors, we should at least know what one is. So I'll start with a simple question. If I multiply a vector by a matrix, what do I get? Another vector. Now, when that matrix A is square, same number of rows and columns, then X and B have the same size. So we can draw or imagine them in the same space. Let's take an example. Here I have a matrix A and a vector X. So in general, when I multiply a vector X by a matrix A, it's going to change both its direction and its magnitude. So here is the vector X in red and the vector AX is in blue. It was transformed by multiplication by A. Now, for all square matrices, you can have special vectors where multiplying that vector by that matrix will change only its magnitude and not their spanning direction. So here I have the matrix A, the vector X, and when I multiply A times X, I get a vector that looks like a scalar multiple of X. So all this multiplication and addition I did with this matrix vector multiplication had the same effect as if I had just multiplied X by a scalar number. And that is the definition of an eigenvector for a given matrix. So for a square matrix A non-zero vector X is called an eigenvector of A if multiplying by A results in a scalar multiple of X. So this is the very famous eigenvalue equation. A times X is equal to some scalar, lambda, times X. That scalar, lambda, is called the eigenvalue associated with this eigenvector. So in this previous example, we had our A matrix and our X vector, and when we multiplied A times X, if we compare what we started with, 1, 3, and what we ended up with, 2, 6, we see that what we ended up with is just 2 times 1, 3, what we started with. So the eigenvalue in this example is 2. And that's the eigenvalue associated with this eigenvector. And that eigenvector is associated with that matrix. So here's another example. Show that X is an eigenvector of A and find the corresponding eigenvalue. Well, what we need to do is simply multiply A times X, find the result, and determine what scalar multiple this result is of what we started with. And the answer would be, of course, -3. Now we can draw these. There's X, and now AX goes in the opposite direction 3 times the length of X. Let's get some practice here just to make sure that the concepts are sinking in.